So we are to the mass spec portion of chapter 21. Now, if it were up to me, I would have taken the first half of chapter 21 about the chromatography, the principles of chromatography portion, and combine that with all of chapter 22, because all of chapter 22 is about chromatography, and then so that would be chapter 21, and then mass spec would be its own chapter as chapter 22. Well, they didn't ask me. There's logic in both ways. So what I'm warning you is we're taking a left turn here. So we're going to talk about mass spectrometry, which is another method of making measurements. So chromatography was all about separating mixtures, and mass spec, we're doing something different. Okay, we're not separating a mixture, we're identifying their masses. So in mass spec, which is sometimes abbreviated MS, what we're doing is we're trying to find the masses of atoms or fragments. Okay, so molecules or fragments are really what we're looking for. Now, what's great about mass spec is it's very sensitive, so low concentrations, it can measure those. And what's great is that with chromatography, when we're trying to separate them, the only way we can really tell is by looking at the chromatogram and looking at their retention times to see if, the number of compounds. But if we have two compounds that have the same retention time, we would never know because we would just have one large peak that both compounds would come out at the same time and we'd have our peak. Okay, well, mass spec is able to take a bunch of different compounds, molecules, all mixed together and separate them out, not separate them, but measure information about each of them. Okay, so how the mass spec works. We take our sample of whatever our compound is, and it's converted into ions. And we're going to talk about specifically how that happens in the next video, how they're ionized. But for right now, just go with their ions. So they've got a charge, so they can be influenced by, voltage, pluses and minuses. Okay. And so these are now, like I said, they're ions. So they have a mass to charge ratio. It's mass in like AMUs divided by its charge. Well, if it's a +1, then it's whatever its AMU is divided by +1. So its mass to charge ratio would just be the positive value of the mass, whatever. But what's great is the mass spec is able to take that sample with a whole bunch of different molecules, make them all into ions, and then separate them, like sort them into their different mass to charge ratio categories. So we're going to look at the last video in this chapter is going to look at the different types of mass spec. So I'm going to start by talking about the transmission quadrupole type of mass spec. It's the most common one. So how this buddy works. So here's our sample coming in. Bam. These little black thingies we're going to talk about later, they're electrons, or in this picture, they're electrons. And so we're making it into ions. So right there, they become ions. Okay. Now here's the quadrupole. There's 1, 2, 3, 4 poles. So it's very literal. Now, if you look on these poles, 2 of them have pluses and 2 of them have minuses. So remember, the things that are going to be after the black rain, which are electrons, they're now ions. And so they're going to be attracted and repulsed with positive and negative charges. So what happens are these poles are set to a certain voltage, and then the radio frequency in there is alternated. And so what happens is these ions are being attracted, repulsed, attractive, repulsed, attractive, repulsed. That's why when you look right here, we see kind of a wave pattern. They're being pulled towards one, pushed away, pulled towards one, pushed away. And so one way to think about this, if we have like a shoebox with the lid taped on, okay, so we can't open it. We cut a hole at one corner, and then directly opposite it, we cut another hole. And we put a little like bouncy ball in there. And then we take the box, and after it's placed in there, we have it flat on my hands, so it's parallel to the ground. And then I take my hands and I rock the box back and forth, left, right, left, right, left, right. Well, that ball is gonna, go to one side and then go to the other. As I rock the box, the ball is going to be rocked along with it, and eventually it will make its way out the hole at the other end. And so that's kind of what's happening here, other than it's not a box and it's not a person, it's charges and ions, but it's rocking it back and forth. And then this radio frequency that it's using is directing a certain mass to charge ratio to so that way it exits through the hole. So if we have let's say 6 different compounds that all have there's 6 different ions, they have 6 different mass to charge ratios. Based on the voltage that are on these 4 quadrupoles, that voltage would be specific to one of the mass to charge ratios. And then the radio frequency would be alternating to make it have its little waves, but then direct it so it goes out the hole. And then as soon as that sample is done, the voltage on the 4 tubes changes to a different mass to charge ratio voltage. And then the radio frequencies get the ions to be directed out of the hole. Now, once the ions leave that, it goes into the detector, which we'll talk about later, which is called an electron multiplier ion detector. The good news is that it works like the photomultiplier tube from the UV vis. So that's great. So typically, mass specs are attached to gas chromatography instruments, which you're going to learn about more in chapter 22. And again, one thing that's great about this, if one peak in chromatography contains more than one compound, the mass spec is able to tell us that. So what happens is all the compounds that come out from that peak get bombarded with these ions, these ions have a mass to charge ratio, and then it separates them out into those mass to charge ratios, and then we're able to get that information. So the voltage, this is saying that first they're sped up. So they're moving quickly by the time they get into there, and then the quadrupole works to separate them. The four rods with a constant voltage and an oscillating radio frequency. So the voltage is constant for one mass to charge ratio, and then it would change for another one. This is all controlled by a computer, so no one's sitting there like changing the dials or anything. That's good news, I think. So, like I mentioned before, the radio waves are alternating to make that wave-like trajectory of the ions. For the one mass to charge ratio that we're interested in that moment, it'll make it so that when that one exits the hole going to the detector. All the other mass to charge ratio ions are just going to smash into something else. They're not going to get it to the detector. They're going to run into one of the quadrupole rods. It's going to run into the wall. I don't know. It just doesn't get through the hole. Okay. And again, the voltage of the rods change based on the mass to charge ratio you're looking at. And this is very sensitive in that it can separate fragments or molecules with a mass to charge ratio difference of 0.3. So think like 0.3 AMUs, which is very, very, close together.